All right, if you're a C programmer, you get it. You love the power, the raw control, but you also know the headaches, right? The manual memory management, chasing down those pesky resource leaks. Well, what if I told you there's a language that gives you all that C performance but just automates away the dangerous stuff? Yep, that's modern C++. And today, we're going to build that bridge to get you right over to it.
Okay, so let's just clear the air on something right now. If you're thinking, oh, C++, that's just C with classes, I gotta stop you right there. You're thinking about the C++ of like decades ago. And look, for a while, that wasn't a bad take. But today, it's a whole different world.
You see, starting back in 2011, C++ went through this massive renaissance. The language has been totally transformed. It's built on a new philosophy that's all about making your code safer, way more expressive, and even more powerful, often at the same time. Let's dive into what that actually looks like.
So our first pillar is what I'm calling automatic safety. The whole idea here is to let the language and the compiler take care of all those risky, bug-prone tasks that in C are all on you to manage perfectly every single time.
The secret sauce behind this is a principle called RAII. It stands for Resource Acquisition is Initialization. I know, it's a mouthful, but the concept is pure genius. You just tie a resource, like a file handle or a block of memory, to an object. When the object gets created, its special constructor function grabs the resource. Then, when the object is no longer needed and gets destroyed, its destructor function automatically releases it. That's it.
And this, right here, just paints the perfect picture. On the left, you've got the classic C dance. You open a file, and then you have to be so careful to close it everywhere. You have an error check? Gotta close. You return early? Gotta close. It's so easy to miss one, and boom, resource leak. But look at the right, the modern C++ way. We just wrap that file handle in an object, let's call it a file guard. And now, C++ does the work for us. The file is absolutely 100% guaranteed to be closed the second that object isn't needed anymore, no matter what.
And that's the beauty of it. All you do is declare that one line. The constructor opens the file for you, and the destructor, which the compiler calls for you automatically, closes it. It practically makes resource leaks a thing of the past.
Now, we can apply this exact same idea of automatic safety to what is probably the single biggest source of pain in C, memory management. And modern C++ has the perfect tool for the job, smart pointers.
So smart pointers come in a couple of main flavors. First up, unique pointer. This one's all about exclusive ownership. It's like having the only key to a house. You own it, nobody else does. When you're done, the memory gets freed. It's super fast, super simple, and incredibly safe. Then you've got its cousin, shared pointer. This is for when you need multiple parts of your code to co-own the same piece of memory. It works with a little reference counter. Every time a new pointer wants access, it adds a tick. When one is done, it erases a tick. Only when that counter hits 0 does the memory actually get cleaned up.
Okay, so C++ helps us write safer code. But you know what? It also helps us write cleaner code. And that brings us to our second pillar, expressive power. This is all about writing code that says what you mean, letting you do more with fewer lines.
This is such a great example. Just looping over a collection. On the left, you've got the good old C-style for loop. It works, of course, but it's kind of clunky. You have to juggle the index variable yourself, and we've all made an off-by-one error there before, right? Now look at the modern C++ version on the right. It just reads like plain English, for each name in names. It's cleaner, and it's literally impossible to make an indexing mistake. And what if you just need a quick little function for a one-off task? Well, since C++11, we have Lambda expressions. They're basically tiny nameless functions that you can write down right where you need to use them. No more fuss with defining a whole separate function just for one little thing. And lambdas really open up a whole new level of flexibility. You can just pass them around like any other variable. They're amazing for things like defining a custom sort order on the fly, handling a button click, or kicking off some work on another thread. So let's talk about a classic C problem. You have a function, but maybe it can't always return a valid answer. What do? Return a special number like -1, or maybe a null pointer. The problem is, the person calling your function has to remember to check for that specific magic value, and it's so easy to forget.
Well, modern C++ has a much more elegant solution for this, called std optional. Just think of an optional int as a little box. That box either contains an integer or it's explicitly empty. The possibility of no value is now baked right into the type system itself, making it impossible to ignore.
And check out how clean this makes our code.
With this slick if syntax, we can do three things in a single, beautiful line. We call the function, we create a new variable to hold the result, and we check if that result actually has a value inside it. It's safe, it's super clear, and it's just so much better.
All right, so we've got safety, we've got expressiveness, but I know what you're thinking, especially coming from C. All these fancy features must have a performance cost, right? And that brings us to our third, and maybe the most critical pillar, performance. The philosophy here is simple. Get all the modern safety, but with C's blazing speed.
One of the coolest tools for this is the const XPR keyword. This is basically a message to the compiler saying, hey, you're smart enough to figure this out right now during compilation, so do it. This lets us create what we call zero-cost abstractions. The feature is there in the code, but it has zero impact on runtime speed.
Look at this example. That power function gets run by the compiler. The result, 16, is just burned directly into your final program. When a user runs your application, there's no function call, no math happening at all. It's just the number 16. It's the raw performance of C, but with much more powerful tools at your disposal.
And for squeezing out performance at runtime? Well, modern C++ makes concurrency way simpler. You don't have to fiddle with complicated, low-level threading APIs anymore to really use all the cores in a modern processor.
And here's the real magic. With just one line of code, stdasync can launch a heavy calculation in the background. It immediately hands you back this thing called a future, which is kind of like a receipt. You can keep doing other work, and then whenever you're ready, you just say, hey, I'd like to cash in my receipt now, and you get the result. It makes parallel programming so much more approachable.
Okay, so let's zoom out for a second and take a look at the bridge we've just laid out from the world of C to the world of modern C++.
It really all comes down to these three pillars. You get automatic safety with RAAI and smart pointers, which just wipes out whole categories of bugs. You get expressive power with features that let you write code that's cleaner and easier to understand. And you get all of this without sacrificing performance, using modern tools to get every last drop of speed.
So yeah, this is not your father's C++. It's a modern, powerful language that has learned so much from its past to become safer, more expressive, and as fast as ever. So the only real question left is, which one of these pillars are you going to use to start building your bridge first? Thanks for watching.